Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, welcome to week 1 homework tutorial. So the homework solutions have been posted, but I'll be using these tutorials just to go through the solutions quickly, make a few points that maybe don't come out clearly on the homework solutions themselves. So let's dive into problem 1. Problem 1 had to do with taking some measured data from a N-channel MOSFET and extracting some key performance metrics. Actually, you were only asked to extract one, the subthreshold swing. So to do that, we look at the plot that is labeled, that is known as the transfer characteristic. So what is the transfer characteristic? Well, it's a plot of the output current, the drain current, versus the input voltage. And this output current is typically measured in microamps per micrometer of width of the MOSFET, because it just scales with the width. So if it's twice as wide, we get twice as much current. And the voltage, gate voltage, is measured in volts. It goes from 0 to the power supply voltage, which in this case was 1.2 volts. And I think the tick marks in this particular plot were 1/10 of a volt. So let's call that 0.1, call that 0.2. We have two curves here. Both are drain current versus gate voltage, but the first one, the one on top here, is done with a drain voltage equal to the power supply voltage, also the maximum gate voltage. And the second one is done with a drain voltage that's very low, say 0.05 volts. So we typically plot only the low drain voltage and the high drain voltage case. And we get characteristics that look like this. The current goes exponentially with gate voltage below threshold, and then above threshold it starts to increase linearly with gate voltage. Now, one of the key parameters for a device is this thing we call subthreshold swing. You know, we measure it in millivolts of gate voltage versus decade or factor of 10 increase in drain current. And we could do it in principle for either one of these two curves. We could get a subthreshold swing under low drain voltage, or we could get a subthreshold swing under high drain voltage. We're most interested in the value under high drain voltage. Now, in a well-designed transistor, these two curves are parallel, so we would get the same answer from both. But it's a better practice to take it off of the high drain voltage regime. And typically we look in a region where these two curves are parallel, and what we ask ourselves is, if we increase the drain current by 1 decade, that's a factor of 10, how much change in gate voltage does that take? So we simply read off the gate voltage, say from 10 to the minus 2 microamps per micrometer. We read off the gate voltage at 10 to the minus 3. And we take the difference between those two gate voltages, which, if you eyeball this curve, is something a little bit less than 100 millivolts of gate voltage, will give us a factor of 10 increase in drain current. So in this particular case, we get something that is roughly 100 millivolts of gate voltage, gives us a factor of 10. So our subthreshold swing is roughly 100 millivolts per decade. If you do it a little more carefully, you find out it's 85 millivolts per decade. Remember, the fundamental limit, the best a MOSFET can ever be, based on the physics of how the current flows, is 60 millivolts per decade at room temperature. So the value that we read off carefully, 85, is not too bad. It's relatively close to the fundamental limit. Okay, there are many other device metrics that you can pull off of these curves. They're listed in the homework assignment, and the homework assignment, the solutions itself, goes through some of those. It's good to familiarize yourself with how you extract on current, transconductance, off current, output conductance, and things like that, because we'll be talking about those concepts over and over. So that's it for problem 1. Okay, let's move on to problem 2 now. So problem 2 involves a little bit of derivation. And the basic idea is that we're trying to relate the sheet carrier density in the number of electrons per square centimeter to the location of the Fermi level in the semiconductor. And you'll recall that what's important is how close the Fermi level is to the bottom of the conduction band. And the key parameter is this separation in energy, which we write as eta sub f. It is the Fermi energy minus the bottom of the conduction band in units of kT. So you can see in this particular example, eta f is negative. If the Fermi level is above the bottom of the conduction band, eta f is positive. Now, you may recall that the answer is that the carrier density in units per square centimeter, since this is a problem assuming two-dimensional electrons, like the electrons in the inversion layer of a channel, the sheet carrier density is a set of constants involving effective masses and things like that, times the Fermi-Dirac integral of order 0 with argument eta f, which tells me where the Fermi level is. So this is a basic relation we're going to be using frequently, and it involves these Fermi-Dirac integrals, which get a little bit complicated. So I want to walk through this once, and you'll see how you work with Fermi-Dirac integrals and how you derive expressions like this. Just a reminder, when eta f is very much less than 0, when the Fermi level is well below, a few kT or more below the bottom of the conduction band, then all of these Fermi-Dirac integrals just reduce to exponentials, and this just becomes e to the eta f. Okay, how do we do this derivation? So we begin with the basic relation between carrier density and density of states and Fermi function. So the probability that a state is occupied is given by the Fermi function. The number of states at energy E is the density of states times dE. We integrate from the bottom of the conduction band. We can go ahead and integrate to infinity. We should integrate to the top of the conduction band, but the Fermi function will assure us that by the time we get there, well before we get there, the Fermi function will be infinitesimally small, so we can just let the integral go to 0, or go to infinity, I'm sorry. Okay, so we remember that the two-dimensional density of states has a simple form. It's effective mass over pi times h bar squared. There's a valley degeneracy that we can't forget about, the number of equivalent valleys at this energy. And this is a step function, so it's 0 until we hit the bottom of the conduction band, and then it's constant. So I can rewrite this expression. These are all constants. I can bring them out front, take them out of the integral. Then I have an integral. My Fermi function is 1 over 1 plus e to the Fermi energy minus the energy of interest over kBt. And then we're integrating with respect to e from the bottom of the conduction band to infinity. So that's the integral that we have to work out. And if we do that, we'll have our answer. So it's just a matter of doing some algebra and being careful about how we do that. So we have this set of constants, which I'm just going to write this way to save myself some time. If I integrate now, I'm going to, in the argument of my integration, I'm going to subtract the bottom of the conduction band and then add the bottom of the conduction band, and then I had a minus energy over kBt. Okay, so I haven't done anything. I've just subtracted and added the bottom of the conduction band. Now I'm going to recognize something here. EF minus EC in units of kT, this is just what we called eta sub f to begin with. And I have something similar here. I have minus E minus bottom of the conduction band in units of kT. I'm going to define that also to be something like this. I'm going to define that just to be eta. And eta is defined to be E minus EC in units of kT. So eta is just like eta F, but instead of the Fermi level, we have the energy. So I can rewrite this expression now. N naught, we have those constants out front. We have an integral, dE, and then I have 1 plus, and now I can recognize in this exponential that what I have is e to the eta minus eta sub f. So I have everything in terms of eta, but let's see here. If I do a change of variables, so using my expression eta, I see that d eta is dE divided by kBt. So dE is kT times d eta, and I can write the numerator then as kT times d eta, and now everything is in terms of eta. Now I have to remember my integral. It started with the energy at the bottom of the conduction band. When the energy is at the bottom of the conduction band, eta is 0. So the lower limit of my integral now becomes 0. The upper limit is still infinity. Okay, so let's collect up the constants. These constants out front were the Valley degeneracy, effective mass over pi, h bar squared. Now we have a kT that came from this change of variables. And now I have an integral to do. 0 to infinity d eta 1 plus e to the eta minus eta f. All right, this set of constants out front is what we call the two-dimensional effective density of states. It has units per square centimeter. This integral is one of these Fermi-Dirac integrals. Remember, the definition of a Fermi-Dirac integral involves eta to some power d eta, 1 plus this exponential. We have eta to the power 0. So this we just recognize as a Fermi-Dirac integral of order 0. When we integrate eta out, we're left with the argument eta f. So the result of the integral depends on eta f. Okay, and we have derived the answer. Right? And that answer was choice B on our answer key. I just want to point out one thing. In general, these Fermi-Dirac integrals cannot be done analytically. Some specific ones can be done analytically. This is an integral that we can do analytically. So the Fermi function, the Fermi-Dirac integral of order 0, actually has an analytical expression. It's logarithm 1 plus e to the eta f. That's one of those Fermi-Dirac integrals that we can work out. Okay, so that's our solution to problem 2. All right, let's move on to problem 3. Problem 3 is about the mean free path. And why do we care about the mean free path? It's because we care about the transmission. Transmission, remember, is a number between 0 and 1 that tells us the probability that an electron that enters from the source exits from the drain. And the transmission is related to the mean free path for backscattering by this simple formula. So it's important to be able to deduce what the mean free path is from experimental measurements. And one of the most commonly measured parameters is the mobility. And in a MOSFET, we call that the effective mobility. In this example, we said that the mobility was 250 centimeters squared per volt second. And our task is to estimate from the measured mobility the mean free path. We're told that we could assume Boltzmann statistics. That makes this problem relatively easy. Later on in the course, we'll show how to do it for Fermi-Dirac statistics, and it will involve Fermi-Dirac integrals. Okay, so, how do we do this? So the way we attack this problem is that we remember that there is a simple relation between the diffusion coefficient and the mean free path. And that simple relation is that the diffusion coefficient is the unidirectional thermal velocity times the mean free path divided by 2. So if we have the diffusion coefficient, then we can easily obtain the mean free path. Okay, well, according to the Einstein relation, which is valid in equilibrium for a non-degenerate semiconductor, the diffusion coefficient is kT over Q times the mobility. So I've been given the mobility, so I can easily compute what the diffusion coefficient is. So we can simply insert this expression for diffusion coefficient in the first equation, and then we can solve for the mean free path. And the result is that the mean free path is 2 kT over Q times mobility divided by the unidirectional thermal velocity. Now all we need to do is to plug in numbers. 2 kT over Q is 0.026 volts at room temperature. The mobility we were given was 250 centimeters squared per volt second. The unidirectional thermal velocity is something that we have to compute, and that is 2 kT over pi times the effective mass. We were given the effective mass, which is a typical value for a silicon conduction band. Plug in numbers, we get 1.2 times 10 to the 7th centimeters per second for the unidirectional thermal velocity. So we put that downstairs. And all we have to do now is to work that out. And if you work that out, you'll find 10.8 nanometers. So one of our solutions, solution C, was 10. That's the closest. So we've estimated that for this particular mobility, it corresponds to a mean free path of about 11 nanometers. Now we know how to compute the transmission of our MOSFET. So that's it for problem 3. Okay, let's finish up with homework problem 4. So homework problem 4 has to do with energy band diagrams. It also has to do with p-channel MOSFETs. So for most of this course, I'm just talking about n-channel MOSFETs. Everything that I discuss applies to p-channel MOSFETs. We just sort of have to invert a lot of signs and change voltages and things like that. So this is a homework problem that gives you a chance to think about that just a little bit. So we have a p-channel MOSFET. Now what does that mean? It means we have a very heavily doped p-type source. P++ means heavily doped p-type. That means that the Fermi level is actually below the top of the valence band in the source. The drain is also p-type, very heavily doped. So the Fermi level is below the top of the valence band in the drain as well. And then the channel itself is n-type. So the conduction band is moderately close to the Fermi level. This is an equilibrium energy band diagram. You can tell that because the Fermi level is constant, uniform across the entire device. Now we're asked, what happens when we apply a large magnitude negative voltage to the gate and a large negative voltage to the drain? What does the energy band diagram look like? And the key to thinking about that is to remember that the potential energy of an electron is minus Q times the electrostatic potential. So minus because the electron has a negative charge. So this is something that we usually discuss in freshman physics, and it's all we need to get the energy band diagram right. So we expect that if we apply a negative voltage to the gate, we're going to change the energy bands in the channel here. And a positive voltage lowers the electron energy. A negative voltage is going to raise the electron energy. If I apply a large magnitude negative voltage to the drain, I'm also going to raise the energy in the drain. So you can sort of see what's going to happen with the energy band diagram when that happens. Now, it's important not to get confused about hole energies and things. These energy band diagrams are plots of the electron energy, potential energy versus position. So the valence band is the potential energy versus position of electrons in the valence band. Same for the conduction band. Okay, so we're talking about electrons here with the negative sign. All right, let's see how this works out. So we have a Fermi level in the source. So let's assume that I'm grounding the source. I'm not applying any voltage there. So nothing is going to change over here on the source end. So the Fermi level is here. You know, the valence band is where it was. Nothing has changed in the source end. Let me redraw this so that we can see that a little bit better. Okay, there's my Fermi level in the source. There's my valence band in the source. Okay. Now, the negative gate voltage is going to raise the potential energy. Let me not worry about the conduction band, because for a P-channel MOSFET, all of the action is occurring in the valence band. So let me just plot this bottom line here. So the negative gate voltage will pull that energy up, and I'll just have a much smaller potential energy barrier. If I'm thinking about this as my energy barrier for holes, barriers will go down for holes, then I have a much smaller energy barrier because of that negative gate voltage. Okay, if I apply a large positive voltage to the drain, then I pull the valence band in the drain way up. So we have to pull the valence band in the drain way up. If the drain is heavily doped p-type, then its Fermi energy will be the same distance below the valence band as it was in equilibrium. And we'll have a Fermi level in the drain that is different than the Fermi level in the source. Okay? So that's how we can tell that the semiconductor is out of equilibrium, because the Fermi level is no longer constant. And those of you who know something about quasi-Fermi levels will know that if you solve the semiconductor equations, the Fermi level makes a transition from its value in the source to its value in the drain, and we call that the quasi-Fermi level. The splitting of these two Fermi levels happened because we applied a large drain voltage. So it's just Q times the drain voltage is the magnitude of that splitting. So this is what the energy band diagram looks like. We have lowered the potential energy barrier for holes. So that's what the negative gate voltage did. Holes can now hop over their potential energy barrier, flow across the channel. We've raised the energy in the valence band, so the holes will just fall down in energy or up on this plot, because this is a plot of electron energy, and flow out, and we've turned our device on and it's operating. So this was choice D, and that's what the energy band diagram for a P-channel MOSFET in the on state looks like.